All right, now that we learned the basics from the inverse sine function, we can look at the inverse cosine function, which honestly is a little bit easier to deal with because when we restrict the domain of the cosine function, we're not going to end up with any negative values. We're only going to end up with positive values. So we can see that with the cosine function, the easiest thing to do, and the thing that we will do, is we will restrict the domain of the cosine function to be between 0 and pi. So when we do this, we of course create a one-to-one function whose domain is 0 to pi that does actually have an inverse. So we will define the inverse cosine function to have a domain of -1 to 1 and a range of 0 to pi. All right, and again, this means that whenever we evaluate the inverse cosine function, our result has to be some number, right, some angle that's between 0 and pi. And then again, there's your equivalence relation, right? The inverse cosine of x equals y is the same, right, is equivalent to saying the cosine of y equals x. So again, we have this alternative notation for the inverse cosine, arc cosine. So just as with the inverse sine, those two notations are interchangeable. And then again, we have our inverse function properties that say that if we take the cosine of the inverse cosine of x, we get back x as long as x is between -1 and 1. And if we take the inverse cosine of the cosine of x, we get back x. And again, this was the important piece, as long as x was between 0 and pi. So this is not always going to be x. It's only x if x starts out between 0 and pi. So we'll look at a couple of those again shortly. So there's your graph. And again, I tend to look at the graphs of the original trig functions and not the graphs of the inverse trig functions. When I try to evaluate them, I think it's easier to do it that way. But I mean, if you want to see it, here's the graph of the inverse cosine function, right? So you can see it starts out at -1 pi, and then it ends down here at 1 comma 0. So here's one of these deals where, all right, if we're trying to take the inverse cosine of the cosine of 2 pi over 3, 2 pi over 3 is in fact in 0 to pi, right? It's between 0 and pi. Therefore, I can use just my cancellation property, and I would just get 2 pi over 3. They call this the cancellation property. I prefer to call it the inverse property. Because what is an inverse? It just undoes whatever the original function does. Okay, so when I take the inverse of the cosine, after taking the cosine, they undo each other and I get 2 pi over 3. Now the problem with this one, of course, is this is not in 0 to pi, right? 5 pi over 3 is outside of that domain. So this would have to be a two-step one. So what they do is they realize, hey, well, the cosine of 5 pi over 3, this has a reference angle of pi over 3, but it happens to be in the fourth quadrant. And in quadrant 4, cosine is positive. So it's actually going to be the same as the cosine of pi over 3, and the cosine of pi over 3 is a half. So that's where they get this a half from. They're just taking the cosine of pi over 3, and then when you take the inverse cosine of a half, you get the angle between 0 and pi whose cosine is a half, and that happens to be our original reference angle, which was pi over 3. All right, so this is an example where we don't just get back x, right? Because we started with 5 pi over 3, but we got back pi over 3, and the reason for that is 5 pi over 3 is not in that interval between 0 and pi, okay? And now I just give you a bunch more examples. And again, when I do this, I tend to think of the restricted cosine graph. So there's my restricted cosine graph, right? It starts out at 0, 1 and ends at pi comma -1, and it passes through that point pi over 2, 0. So now that I can look at this, the thing that you've got to realize, though, if you're looking at the restricted cosine graph as opposed to the inverse cosine graph, when I'm trying to evaluate these inverse cosine functions, I'm not finding a y value, I'm actually finding the x value. So what I'm going to do is I'm going to realize that inverse cosine of 1 means, well, where is the cosine equal to 1, right? So in other words, where is y 1? Well, y is 1 right up here when x equals 0. So that's the difference, right? I'm actually finding x values here on this curve when I'm looking for the inverse cosine. right? So when I'm evaluating the inverse cosine of 1, I'm finding the x value that gave me 1. So which x value gave me a y of 1? 0. Which x value gives me a y of negative 1? Well, negative 1 is down here. Which x value gave me that? Well, that would be pi. Which x value gave me a y value of 0? Well, here's where y equals 0. Which x value gave me that? Pi over 2. Okay? Now here, inverse cosine of a half, well, I know it's a half right around here, so it's got to be between 0 and pi over 2. So what I need to find is the reference angle whose cosine is a half. So which reference angle has a cosine of 1/2? Well, that would be pi over 3. And in this case, my angle is between 0 and pi over 2. Therefore, my reference angle is actually my value here. So that's actually going to be pi over 3. Now here, which angle has a cosine of negative radical 2 over 2? Well, that's going to be down here somewhere between pi over 2 and 0. So I have to, again, find my t bar, right, my reference angle. So in this case, my t bar would be pi over 4, because the cosine of pi over 4 is going to be the square root of 2 over 2. But I'm actually going to be in this second quadrant here between pi over 2 and pi. And in the second quadrant, the angle that has a reference angle of pi over 4 is 3 pi over 4. And again, if you want to check this, you can check it, right? You just check it by then saying, well, what's the cosine of 3 pi over 4? And the cosine of 3 pi over 4 is negative 0.7071. And I would just have to make sure that that's equivalent to the negative square root of 2 over 2. And when I punch that in, I get the same value. So this works. All right, so the inverse cosine of negative radical 2 over 2 is actually 3 pi over 4. Now, inverse cosine of negative square root of 2, well, the negative square root of 2 is like negative 1.4-ish, right? So this cosine graph never gets below negative 1. So again, this is undefined because it's not in the domain. Negative square root of 2 is not in the domain of the inverse cosine function. Now, inverse cosine of 0.4, well, this 0.4 is actually 2/5, but still, this is not one of our trig wheel values, right? So I would have to just punch this in my calculator. Now, I know the result of this would have to be between 0 and pi over 2, because 0.4 is like right here, right? So the result has to be between 0 and pi over 2. So that kind of gives me a little hint, but I would just do inverse cosine of zero point 0.4, and I would get 1.1593. So this is approximately 1.1593, and that makes sense because pi over 2 is like 1.57-ish, right? So this is 1.1593. And then inverse cosine of negative square root of 3 over 2, well, again, I have to find my reference angle, and my reference angle, right, my reference angle for a half was pi over 3. My reference angle for radical 3 over 2 is going to be pi over 6. But again, this is negative, meaning I'm going to be down here, so I'm going to be in the second quadrant. So which angle in the second quadrant has the reference angle of pi over 6? That was 5 pi over 6. And again, you can be referencing your trig wheel in these problems, right? Until you get really comfortable with the trig wheel, it's probably a good idea to reference it, because each time you reference it, it's just like studying it more, and then it'll eventually become part of your long-term memory, and you'll be able to recall these easier without having to reference the trig wheel. So inverse cosine of negative radical 3 over 2 is actually 5 pi over 6.